Hello everyone, welcome back. Before we dive into the technical details, I want to tell you what inspired this video. Earlier today, I was talking with a friend, and somehow our conversation drifted toward containers. As often happens, one simple question came up. What's really the difference between a virtual machine and a container? It's one of those questions everyone seems to ask at some point. That conversation reminded me of something that happened at work a while ago at WDSECAP. We had one of those meetings that wasn't on anyone's calendar. The kind that there is an architectural decision to make. It affects multiple teams, and suddenly people from R&D, development, infrastructure, and support are all sitting in the same meeting trying to figure out the right direction. At the time, we were evaluating whether moving part of our platform to containers and Kubernetes actually made sense. Not because Kubernetes was popular, but because we want to understand whether it was the right technical decision for our environment. During that discussion, our CTO asked a simple question. What do you really gain by moving from virtual machine to containers? Not just moving, but what we really gain by using containers. What I found interesting wasn't the answer. It was that everyone answered from a completely different perspective. The developers immediately started talking about CI/CD, portability, deployment microservices, and developers' productivity. The infrastructure engineers talked about operation, automation, and maintenance. And the support engineers were actually thinking about troubleshooting, upgrading, and production incident. Uh, I realized during that time that I was looking actually at the problem from entirely different angle. That's one of the things that I enjoy about engineering. Very few questions have an absolute answer. Your background always going to shape the way you analyze a problem. So the same thing happened actually also in performance engineering, since this channel is dedicated to system administration and performance troubleshooting. Um, if we think about how, because performance engineering is usually done by multiple teams. For example, let's say you have an issue, and this issue you don't know exactly where where it started or where it is reside. Multiple team have to intervene, so you can find exactly what is the issue is. Usually the database team and the system administrators and the developers, and each group or each team is going to have a different perspective. For example, let's say the developers usually are going to check uh, the workload, or they're going to do a workload analysis. They're going to start from the code and from the libraries, the compiler, etc. But system administrators or performance engineers often start somewhere else. They ask different question. They usually try to check the resources usage, and the question will going to be like, how are the hardware resources being used? Where is the CPU spending its cycle? Where is the memory allocated? Is the access local or remote? We talked about those kind of things briefly at the earlier sessions, but we are going to take our time and other videos also. But anyway, I'm not saying that there is a better perspective, or neither perspective is wrong. But simply each one is going to answer different questions. That's also why I wanted to make this video. There are already hundreds of videos explaining the difference between virtual machines and containers. Most of them are excellent, but almost all of them approach this topic from a software development perspective. I want to approach from the perspective of Linux performance engineer, because once you start the investigation production system, you stop asking whether the container are lighter. Instead, you are start to go on to ask different questions like how many address translation happened before the CPU reaches DRAM, where is the memory actually allocated, what happened to the TLB, how does NUMA affect the workload, what changed when we replace the guest kernel with namespace and C groups, those kind of stuff. So we already spent some time trying to in this channel trying to understand virtual memory or application memory, page table, the MMU, the TLB. We did some lab also. We did a lab about it. So we're not going to compare Docker command or Kubernetes manifest. Instead, we are going to follow a single memory access. Actually, maybe we are not going to go this far, but yeah, we are trying to understand what is from a performance engineer perspective, what is the difference between a virtual machine and the container. Okay, so I want just to make sure that we are all on the same page. Let me maybe not this one. Okay, let's take this one. So we talked about how a process have something called VMA, like we are seeing here. For example, the first VMA is the text, the heap, it should be from down upward, the stack, and it can have shemam, shared memory. So this is what the process actually seen. The process thinks that it has all the system. Let's say this is your server, this is your server. The process just think that it has all the resources in the server, that nobody is sharing the system with it. So the developer won't be concerned about the multitasking, etc. This is going to be taken care of by the kernel. Okay, so and we did actually talk about the difference between a multi-process and multi-threading. We said that the difference, for example, the thread is actually sharing the text and sharing the heap and the shared memory, but the only thing that they have different, which is the stack. You'll find here there is multiple stack. So they share basically the same virtual memory space. Okay, so this is going to help us later, but for now, let's say, as we said earlier, that let's say this thread is trying to access a new uh, or to use malloc to access memory. Okay, malloc. So what's going to happen is going to first of all do a reservation. Reservation is just the OS is going to promise the process that you got it, you got what you asked for. But after that, when star do an allocation, what's going to happen? The MMU, okay, sorry, there is something called TLB misses, since this is the first time you're going to ask to access this page. So we don't have the physical address. What's going to happen? There is an exception raised. The OS is going to take over. Then after that, the MMU is going to do a walk. Let's say, imagine this part is where the page table resides. So MMU is going to do a walk page table, and at the end, after what's called the PGD, the POD, the PMD, there is something called PTE at the end, and this PTE is going to point to the physical address. So after that, we are going to load the physical address to the TLB. So what we are going to have is we are going to have a virtual memory to physical memory translation. Physical memory translation. Okay. So the next time the process, when it try to access the same virtual memory, is going to have the same physical memory already exists. So when is another thread, let's say thread 2, is trying to access the same virtual memory is going to point to the same physical memory. But this is not going to happen when you are talking about multi-process service. Let's say we have different one here. This is another process. You might have the same virtual memory, but this same virtual memory is definitely pointing to a different page or physical memory, since they are not both sharing the same VMA, virtual memory address, okay, or virtual memory space. I hope this the difference is clear here, because actually this is going to help us next when we are trying to explain the difference between virtual memory and the container, virtual machine and container. Okay, so we now know that if we have multi-threading process, they all share the same VMA, and each virtual memory is pointing to the same physical memory. Okay, so if we go to, let's say here, and we have, let's say, this server with multiple NUMA node, you have to know that this there is two things, two NUMA topology. When we are talking about bare metal, we have the hardware NUMA node or the physical NUMA node, physical NUMA, and we have something else called host NUMA. Usually they both are the same, but sometimes, let's say in AMD architecture, you'll find that in one socket you have four NUMA node for some CPU. Sometimes it is two, sometimes four, but it exists that you're gonna find uh, in one socket it is exposing for NUMA node. So when you do, and this is just a virtual machine, so you're not going to find a lot, but when you do NUMA control dash dash hardware, you'll see, for example, let's take this one. Let's take this one here. In this case, since this is just a virtual machine, but let's say this one is, let's do it like this. Let's say this one is a hardware bare metal bare metal machine. You'll see, for example, there is more than one NUMA node. You'll find here, for example, there is 0 and there is 1, and let's say the distance is 21. And let's say it is 2 NUMA node, okay? Let's say it is 21. What does that mean? Actually, you'll find out that also there is here 1, and here you'll find there is 0, and or 10, not 0, sorry, 10. And here you'll find 21. Usually something like this, 21. Okay, let's see it here. In this case, when you are going, let's say you are a process here, okay, and the thread is working, the thread is working here, and the first touch, as we talk about first touch policy, was here. So when you access from the local memory, is going the distance is going to be 10, which is basically like 1 nanosecond or 7 nanoseconds, something like this. But when you're going to go through the interconnect and to access the memory here, this one is going to be 21. This is the distance is 21. It's 21. Okay. As I was saying, let's go back. Let's go back here. As you can see, there is a node and there is a distance. So we have only two vCPU. and we have only in this VM one NUMA node. So imagine in a case where let's go back here in a virtual machine. Okay, let's start from here. Okay, in a virtual machine, for example, when the for as I said, for the virtual machine is not going to point to the PTE is not going to point to what called physical, let's say physical uh, memory. What's going to point to is something called physical, host physical memory. Since we are in a VM, this is not actually the actual RAM. It is this one. It is a software. What it is? It is exposed by the hypervisor to cheat and to make the OS think that this is an actual RAM, but it is not. It is actually exposed by the hypervisor. Let's say we are using KVM. So KVM and KMU are going to, let's say, and KMU are going to expose the hardware to the guest OS. So the guest OS think this is a memory, but it's actually it is not. So just a simulation. And the PTE is going to point to something called guest, host physical, guest physical memory. And there is something else supported since uh, the new processor, not actually new technology, it is old, but now we have something in Intel called EPT. EPT. Okay, it's not going to work for me. Anyway, it's called EPT. It is not PTE, it's not the same. This one is extended page translation. So, as I said, the PTE is going to point to the guest physical memory, and the EPT is going to do a translation from the guest let's write it here, guest physical memory to host physical memory, which is the actual RAM existed here. If we take this one, let's say this one is actually 1 TB. So the PTE is taken the GPM and point here, actually. And this is supported by the processor. And in AMD, I think it's called the NPT, something. Yeah, NPT. So if we have a NUMA node, as I said, let's say take this picture, not this one. I think I messed up and removed the old one. What is okay? Let's do it again. So let's say we have something like this. Like this. I can do it like this. And this is the hypervisor. Let's say this is KVM, and our OS. So what's going to happen? Let's say this is, as we said, this is our hardware server, and we installed the OS on top of it. We installed the KVM, etc., and we are going to expose some fake hardware to the guest, so the guest can use that OS. This is how the VM works. Let's say this is we have two NUMA node here and the physical server. So QEMU. So this one is called actually this one. If we are going to talk about the type of NUMA node, this one is called physical NUMA. NUMA, as we said. The physical NUMA is just the hardware reality, the actual CPU socket, their memory controller, the distance matrix between the interconnect, etc. So for example, the picture we talked about here, if we have the distance, let's say this is a physical one, the distance is going to be correct. For example, the first NUMA node is 10, the second one is going to be 21, etc. Let's say this one is 41, not let's say it's more than one the two NUMA node. This one is 41, and this one is actually 41, and this one is 10. Okay, let's say we have 4 NUMA node, for example. So in this case, the distance are going to be correct, etc. The OS is going to read it in some way. Let's say, as we said, if this is going to be AMD, there is some processor in AMD exposed for NUMA node. So you might see 8 here. But let's say we are going to see the same number, so we don't make it complicated. Usually this is how it happens, okay? This is called actually what the OS is seeing, or what the OS exposing is called host NUMA node. Host NUMA node. It's not physical, it's host NUMA node. Then we have something else called virtual NUMA node. What does that mean? What the OS or the KVM is going to expose. This one is called virtual NUMA node. So to the guest, it's like the host, the physical NUMA node. I mean, to the guest, if we do it like this. Okay. So when you're creating a VM here, the VM is going to see the virtual NUMA node. It's not going to see the physical or the host, but also the OS inside this guest is going to see and report this driver from is going to expose it in different topology. This one is called guest NUMA node. Guest NUMA node. Okay, so we have 4 type of NUMA node right now. The problem is, let me remove this. The problem is this OS is going to make some decision based on NUMA node that are not real. For example, let's say here for this guest VM, we have, for example, this NUMA node 0. It might be pointing to this NUMA node. And this NUMA node is pointing to this NUMA node. We're going to make it simple because it is more than that. Sometimes when there is no space, you might find one NUMA node spread into 2 different NUMA nodes. But let's say it like this. So you might have a thread that is also running here, and also this thread is running here. But in reality, those virtual CPU, let's say, because the VPC is actually inside VPC, inside the host is just a thread. Okay, So let's say those two threads are running inside here. In reality, they are running in two different NUMA nodes. So the decision that is going to be taken by the OS is not actually real, and it shows you here that they are both, for example, let's say the memory here that those two threads are accessing are distant, but in reality the memory is here, for example, and one of them is accessing it locally. So I think you get the picture. So this OS doesn't have any idea what really happened inside the server, or how the hypervisor is dealing with the threads. Okay, so in case there is something called in Linux, there is something called AutoNUMA. What this is going to do, for example, let's say your workload, for example, let's say you have here in the guest, let's say this is what the guest is seeing. Let's say you have two threads are running inside the same CPU, not two thread, but there is many, let's say, and you when you see when the OS is going to find that the workload is not balanced between those two NUMA node, and it is more than 25% more. This one is more 25% more than this one. What's going to happen is going to change some thread from this NUMA node to this NUMA node. And let's say there is here three NUMA node, but this one is accessing the memory from remote. This is a remote access, but this thread is using the memory more than all of them. What's going to do? The thread is going to change or move the memory from this NUMA node to this NUMA node. Okay, so sometimes this is not going to affect the hardware or the hypervisor, because the hypervisor is making decision based on the actual NUMA node. But there is some things that you need to pay attention to. For example, let's go back here. Let's go back here. Okay. So imagine you have two NUMA nodes, and as I said, the guest is migrating thread from one NUMA node to another. So the memory also, because of the frequent access of that thread. So since it moves that thread from one NUMA node to another NUMA node, and it moves also with the memory, what's going to happen here? The virtual memory. Okay, this is not what I need. Let's take this one. So the virtual memory is going to change from one NUMA node to another NUMA node. Sorry, not the virtual memory. The virtual memory to the guest physical memory, since we modify the pages from one NUMA node to another. So this is going to be changed. So the same virtual memory is not going to point this to the same uh, guest memory, or guest memory. Let me go back here so I can explain it more. So as we said, we have two NUMA node here, and this is the memory. So we are moving some pages from one NUMA node to another. This is the process. This is the process VMA. So let's say this part is not pointing to the same place anymore. It has to point to this place. Okay. And this is because of the AutoNUMA. Okay. And imagine the same thing is happening also in the physical NUMA. So it is happening in the VM. The OS has AutoNUMA, but as I said, it might not affect what's really happening on the hypervisor might ignore that and doesn't affect your workload. But here, the what your CPU is doing actually, your CPU is doing changing here as you see, we talked about it here. It's changing the TLB, and also you have some changes in the EPT. Okay, is something also happen in the physical memory. There is fragmentation, then there is compaction, and you have some pages are moving to another place. You'll find yourself also changing some uh, entries in your PTE, your EPT, excuse me. Okay, so even though nothing has changed in the hardware here, if you go back, not this one, and the best case scenario, nothing has changed here when we moved some data from this memory to this memory. You still have some work to do in the guest of in your guest OS. Okay, your CPU is still busy doing some workload. So imagine also, as I said, there is okay. Let me check my note. Okay, so what is you think the best solution that should be done in this case to make the migration thread? There is no migration thread because I said when there is workload that it is in one NUMA node is more than the other, there is a migration thread. Because of the AutoNUMA node is going to move some thread to this NUMA node, and which could cause some memory to be moving also to this NUMA node. Okay, but imagine you are doing this and you're doing some calculation to change also the PTE and the EPT, and also at the same time your AutoNUMA node on the OS is seeing that there is some workload need to be moved. Maybe for some reason it is also moving something from here to here. Okay, so you have two problems here. You have your guest doesn't have any idea about your hardware, and all the decision that it is made by this guest OS is based on fake NUMA node. Doesn't have anything based on. Okay, so what people are actually, this is the default behavior. By the way, this is when you install a machine and you install a hypervisor, and this hypervisor, let's say it is KVM, and let's talk about KVM, and you will not specify your policy here. This is what's going to happen. You don't know exactly what this NUMA node is represent. Maybe it is this one, maybe it is this one, maybe it is both of those, maybe it is part of this and part of this. You have no idea. Okay, so what people actually are doing, there is something here called policy, as I was saying. Let me this is actually from my book. I mentioned that I'm not going to show you anything because I don't have any NUMA node right now. So we are using something called policy here. Yeah, you see policy bind. And you are checking your NUMA node and say node 0, it should be in memory 0 and CPU from 0 to 31. Let's say something like this. Okay, so what this is going to do, this is going actually to bind your host NUMA node to your guest NUMA nodes. So now you have uh, an idea, or you are making your guest OS have an idea what's really happening under the hood. Okay, so your virtual CPU from 0 to 31 is going to be pinned to the host CPU 0 to 31 socket 0, and your socket 1 is going to have also as such. Okay, in this case, you're aligned your NUMA node inside your KVM to the host, to the physical NUMA node, which suppose what you're going to have on the default configuration when you don't specify your policy. Okay, let's go back. So this is one of the things that I want to talk about to make sure you know the difference between a container and because inside, since containers are sharing the same kernel is going to have the same view of the NUMA nodes. So all the decisions are going to be based on actual, let's say, if you are in bare metal, of course, we're still talking about the bare metal. If you have an actual bare metal server, your kernel is going to be aware of the hardware and based all the decision on the actual hardware, which is going to be way faster, of course. And yeah, so as you know, they all share the same kernel, but they have different view, and you are going to face some complexity because of the security, the SE Linux, the if you are using Red Hat flavor, if you are using Debian, of course, AppArmor, etc. But they all share the same view usually, and they have because they are working on the same kernel. So your system is going to treat the container as it is a normal process. Okay, even though they have different namespace and different, as I said, different C group, etc. So we might have another session talk about the C group and talk about the other stuff. So uh, yeah, but for now, I think you understood uh, what we were talking about and the complexity behind each technology. And yeah, I hope this was helpful for you, even though we didn't talk a lot about containers, but I think explaining what we are having in a virtual machine is actually explaining what we don't have in a container, I think. Thank you guys for watching this video. I'm really happy that you enjoyed, or at least some of you enjoyed some of my videos. Thank you for your comment. Thank you for your thumbs up and likes, etc. I hope you can do the same for this video. Give me some comment also. If you have a question, please ask. And yeah, thank you guys. Bye.